Hello, my name is Nathan Otterness, and in this presentation I'll be giving what I hope is some new information about how AMD GPUs work. But first, to understand why such a thing is useful, one needs to understand how GPU research normally plays out in the real-time community. In a nutshell, the utility of any research, be it an effort at modeling, predicting, or managing GPU hardware, depends on the quality and amount of information available to the researchers. And so far, almost all real-time GPU research targets NVIDIA GPUs, which is understandable because GPUs manufactured by NVIDIA are currently more popular, at least in research, than their counterparts manufactured by AMD. But there's a problem here, a lack of reliable information. NVIDIA GPUs and their underlying software are often described as black boxes, meaning that obtaining information about their behavior, at least as an independent researcher, is much more difficult. This means that many projects that seek to apply the knowledge about NVIDIA GPUs need to dedicate large amounts of time to simply obtaining the necessary information, before working on the true objective of the project. Wouldn't it be nice if there was a way to avoid the information gathering phase of GPU research, and could using AMD GPUs be the answer? For those who don't know why the GPU's manufacturer is even relevant, there are 2 points to consider. First, AMD GPUs have a fully open-source software stack, at least on Linux. This eliminates a large portion of the black box currently hindering real-time NVIDIA GPU research. Second, AMD GPUs offer built-in support for hardware partitioning, even on less powerful consumer-oriented models. Partitioning has the potential to greatly reduce unpredictable contention when multiple tasks share a single GPU. When I said that AMD GPU programming software stack was open source, I was specifically talking about their ROCm software, which is an abbreviation of Radeon Open Compute. ROCm is basically the AMD GPU counterpart to CUDA on NVIDIA, and like CUDA, it consists of a high-level API, a compiler for GPU code, and various underlying user space libraries and driver support. Unlike with CUDA, however, which is generally presented and used as a monolithic entity, the various layers of the ROCm stack are visible to end users, though the distinction between these components is more important in our paper than it is in this presentation. As one would hope, the presence of AMD source code is quite helpful if you want to learn how their GPUs work, though perhaps it's more accurate to say it's quite helpful if you want to confirm how their GPUs work. You see, the problem is that there's a lot of code involved in ROCm. For example, the AMD GPU driver for Linux accounts for nearly 10% of all the lines in the Linux source tree, and the user space components of ROCm aren't small either. Unofficial documentation isn't very helpful if you want to learn how GPUs work. The little documentation that is available mostly focuses on higher-level APIs. So source code may be a good reference as long as you already know what to look for. We intended our paper to be such a starting point, explaining the high-level behavior and supporting it using official sources from AMD, as well as basic experiments. For the sake of time, this presentation only presents the main conclusions. If you want the specific references, you'll need to read our paper. Now that I've explained the motivation behind the work, I'll move on to getting some necessary definitions, followed by our motivating experiment, and finally the explanation of how the GPUs work. For those unfamiliar with GPU programming, you'll often hear me use the term kernel to refer to a section of code that runs on the GPU. As someone who likes OS work, I'll admit that I also found this confusing at first, but it's a common terminology used throughout GPU literature, so I continue to use it here. Second, most of you will already know that the main benefit offered by GPUs is their massive parallelism. When writing GPU code, we often think in terms of GPU threads, in a similar manner to how we think of CPU threads. I'll show an example in just a little bit of how this is used as in an actual program. In reality, however, at least on AMD, threads are just an abstraction that's convenient for writing programs over the GPU's underlying SIMD vector processing hardware. One concept that's especially important in our later discussion is the thread block, which I'll usually just call a block. In GPU programming, a block is a group of threads executing in lockstep, meaning that all the threads that are in a single block must be executing the same instruction at a time, but on different pieces of data. The programmer requests a specific number of blocks when launching a kernel on the GPU, and each block may consist of up to 1024 threads. In our discussion, blocks are so important because they are the schedulable entities on the GPU. In other words, when the GPU is executing a kernel, it is internally assigning blocks to compute hardware. Finally, the term stream is used to refer to a queue of GPU operations, such as kernel launches. Operations enqueued in a stream must complete in FIFO order, and as streams provide this ordering guarantee, they obviously have an influence on how work is scheduled on the GPU. So, to give a quick example, here is how we can write a GPU kernel for a vector add operation that attempts to add many elements of a vector of integers in parallel. You can imagine this code running in a huge number of parallel threads, one thread per vector element. You'll notice that it's only 2 lines. The first line acts as special per-thread variables to determine the index of the vector elements to compute, and the second line simply performs the computation. In order to launch this kernel, we first need to create a stream, remember a queue of commands, in which to enqueue it. For space, we don't show the code for allocating and initializing the vector's contents on the GPU, but we'll assume they're already properly loaded into GPU memory. Finally, we'll launch the kernel specifying the stream into which it is enqueued, and wait for it to complete by calling a stream synchronize function. Note that when we launch the kernel, we need to specify the number of required blocks and threads per block. We don't give the specific values for these variables here, but for this example we would need to ensure that they exactly cover the number of elements in the vectors. Before moving on to our main motivating experiment, we will also describe our test platform. For this paper we used a Radeon 7 GPU which contains 16 GB of dedicated memory and 60 compute units. This paper doesn't focus on memory, but the GPU's compute units, or CUs, are very important for several reasons in our work. For those of you familiar with NVIDIA GPUs, CUs are basically AMD's version of NVIDIA's streaming multiprocessors. They contain the bulk of the GPU's arithmetic and logic processing. Of particular importance is the fact that the GPU assigns each thread block to a single CU when executing a kernel. A single thread block cannot be split across multiple CUs. On top of this, AMD's partitioning support that I mentioned earlier uses CUs and takes the form of a CU mask, basically an optional bit field associated with each stream, specifying a set of CUs that any kernel enqueued in the stream is allowed to use. And while we're discussing our test platform, we'll also mention our software test platform, a GPU-accelerated matrix multiply task. While fancier GPU-optimized matrix multiplies exist, all of our tests simply involve multiplying 2 square matrices of floating point numbers together, using 1 GPU thread per element in the matrix of results. So with those definitions out of the way, we can move on to our main motivating example. After learning what we now know about AMD GPU behavior, we were able to craft a set of tasks with particularly terrible performance when sharing an AMD GPU. While we could have made the paper more directly oriented around best practices, we decided that doing the opposite is likely more interesting. First, showing how bad things get serves as an upfront motivation for why it's important to have correct GPU management. And second, the bizarre behavior in some of these test cases directly reflects some GPU internal behavior in a way that would be virtually impossible to capture when doing things properly. While I already said we're using matrix multiplication, there are a few more details to know before I get to the experiments. Our experiments use 2 different tasks, but both tasks do the same computation: multiply 1024 by 1024 matrices as quickly as possible. Even though these tasks do the exact same computation, requiring an identical number of arithmetic operations, they differ in one aspect. They use a different block size on the GPU. Our MM1024 task uses 1024 GPU threads per block, whereas our MM256 task uses blocks containing 256 threads. Each of our experiments involves 2 tasks, a measured task, for which we record how long each matrix multiply takes, and an unmeasured competitor that runs concurrently on the GPU. And for each combination of measured task and competitor, we also experiment with 3 different partitioning options, which I'll explain in more detail on the next slides. So, as a nice baseline, what happens if we run 2 identical MM1024 tasks on the GPU at the same time, without attempting to partition either task? It turns out that the measured task is able to complete each matrix multiplication in about 6.5 milliseconds, almost exactly at half the rate it can complete the computation without any competitor at all. We include this measurements in the paper. There's nothing strange here yet. Now what happens if we enable partitioning, forcing the measured task and competitor to run on their own independent halves of the GPU's compute units? It turns out that each matrix multiply slows down just a little bit, which isn't surprising given that the task is no longer able to opportunistically run on any compute unit on the entire GPU. So far, there's still nothing surprising. But what happens if we give the measured task a tiny bit more flexibility and allow it to run on one CU from the competitor's partition? Unless you're already familiar with how these GPUs work, I doubt you are expecting its performance to drop by a factor of over 10. And even though we don't give you the numbers, you can take our word that the competitor barely slows down at all, despite needing to share one of its CUs. Clearly, we're doing something wrong here. But there's more interesting stuff to see. So far, we've only considered a competitor that's identical to the measured task. What if we repeat the experiment using MM256 as a competitor instead? If we don't use any partitioning, MM1024 is nearly 3 times slower when competing against MM256 than against MM1024. And not only that, but MM256 doesn't even seem to notice that MM1024 is running. It runs at the same rate that it does when it has the entire GPU all to itself. And if you want to see the data for this, you'll need to check the paper. Finally, we can restore a little bit of sanity. One partitioned MM1024 can run at just about the same speed, no matter whether it's sharing the GPU with MM256 or another MM1024 instance. So partitioning is able to prevent whatever problems that MM256 causes when sharing CUs with MM1024. But if we go back to the uneven partitioning scenario, the bad results have stacked on top of each other, adding up to a 13 times slowdown over 2 MM1024 instances sharing the GPU with no management. So there are clearly 2 obvious takeaways here. First, it's much worse for MM1024 to share the GPU with MM256. And second, our uneven partitioning is clearly a very bad idea. But the real question here is, why does the GPU behave like this? Fortunately, we have the answers, but giving them requires a deeper look at how AMD GPUs schedule work. It turns out that most of the effects from the experiment are due to the GPU hardware rather than software. However, we will quickly need to explain how kernels get from AMD's user space libraries to the hardware to start running to begin with. It shouldn't come as a surprise, but the path that a kernel launch request takes through software is not particularly simple. And I mentioned this earlier, but our paper doesn't cover requests to copy data to or from the GPU. But at least the queuing structure we're about to discuss is also used by memory transfer requests. The starting point for launching a kernel is the API function shown a couple slides ago. This function clearly must enqueue a kernel launch request in a stream somehow, but what does that mean exactly? ROCm's high-level programming API is called HIP, and HIP is implemented using C++. So under each HIP stream is actually a FIFO queue of C++ objects into which commands can be enqueued. So far, these commands and queues are all accessed and managed entirely by user space runtime libraries. Things start to get a bit more interesting when a command reaches the head of the stream's queue. After being dequeued, the command is converted into a lower-level representation that the GPU can interpret, known as an AQL packet. The AQL packet is written into a different queue, known as an HSA queue. Unlike the software queues directly underlying each stream, HSA queues are special in that they are directly accessed by the GPU hardware. Now that we've reached the point of discussing GPU hardware, it's a good time to refine the simplistic image of the inside of the GPU that we showed earlier in the slides. Inside most AMD GPUs, compute units are actually spread into 4 shader engines. So on our Radeon 7, each of the 4 shader engines contain 15 of the GPU's 60 compute units. Each shader engine also includes additional hardware besides compute units, such as these workload managers that we'll discuss later. But for now, the important part of the diagram is the command processor at the bottom. The command processor contains 4 asynchronous compute engines, abbreviated ACE in the diagram, which are responsible for handling kernel launch packets in HSA queues. Having multiple ACEs allows the GPU to launch kernels from multiple HSA queues in parallel. So essentially, the ACE is the kernel dispatch packet's first stop in the GPU hardware. So now that we've reached GPU hardware, I'll pause for a second to mention that there are several more details in the paper that I'm leaving out of this presentation, especially pertaining to the usage of HSA queues. Okay, so a kernel launch request has now been picked up by GPU hardware, so the next step is actually starting to run it. But dispatching its blocks to the compute units takes a little bit more explaining. So for now, we'll just assume that we're considering a single ACE handling thread blocks on behalf of one kernel. The main task of the ACE is to distribute these blocks to the GPU's shader engines. Within a shader engine is the job of the workload manager, which I abbreviate as WLM in this diagram, to choose which CUs the block will run on. However, I need to cover a specific guarantee that AMD makes about block ordering before moving on, as otherwise some of the behavior that I discuss later won't make much sense. AMD GPUs guarantee that blocks with lower numbers are launched before blocks with higher numbers. This is done to enable a producer-consumer relationship between blocks within a single kernel, as higher-numbered blocks can safely assume that lower-numbered blocks have either already finished or at least are currently running. We discuss this further in the paper, but for now the thing to know is that this block ordering guarantee uses the mechanism with which the ACE assigns blocks to shader engines. So I personally like to think of the ACE's behavior in assigning blocks using a metaphor, where the 4 shader engines are people playing a card game and the ACE is a dealer. The ACE will deal the blocks to each of the 4 shader engines, the players, in order, without skipping any of them. We can look at this simple example. The ACE always assigns a block to a shader engine 0, followed by 1, then 2, then 3, before returning to shader engine 0. But what happens if there's a CU mask that prevents some CUs in a shader engine from being used? Well, as long as any CUs are enabled in a shader engine, nothing will change, and the ACE will still always send a block to the shader engine without skipping it. The only time the ACE will not send a block to a shader engine is if all CUs on the shader engine have been disabled by a CU mask. In other words, the ACE will evenly distribute the blocks among the set of shader engines for which any compute units are enabled. So now we've covered the ACE's behavior in assigning blocks to shader engines, but how do the workload managers assign blocks to the compute units? There are 2 things to consider here. First, the workload manager must abide by each compute unit's resource limits, and if multiple kernels are executing simultaneously, the workload manager must also decide which kernel's blocks to run. We'll discuss each CU's resource limits using perhaps the simplest example. For practical purposes, each CU only runs a maximum of 2048 threads at a time. So in the example on this slide, the compute unit is able to start executing one block of 512 threads, then a second block of 1024 threads. However, at this point it is unable to start executing another block of 1024 threads because doing so would exceed its total limit of 2048 concurrent threads. Now for the second of the 2 jobs of the workload manager, multiplexing between concurrent kernels. By default, a workload manager will attempt to assign a block to a CU from whichever kernel least recently had a block assigned to a CU, essentially leading to round-robin behavior. But this behavior changes if no CUs have enough resources to take a block from the least recently assigned kernel. When this happens, the workload manager will instead allow blocks from the other kernel to cut ahead if possible. This is good for maximizing the amount of hardware utilization, but it can be particularly bad for kernels with larger block sizes, as completing a smaller block likely only frees up enough resources to allow another small block to run. And if you want some proof, we can observe this effect on real hardware. Here I've provided some timelines showing the number of active GPU threads over the full duration of a single kernel from each task. On the left, we can see the timeline of 2 concurrent MM1024 kernels sharing the entire GPU. Shortly after the second kernel starts to run, the GPU's resources have been divided roughly in half between the 2 tasks. On the right, we see what happens when running an instance of MM256 instead. Shortly after MM256 begins, it has occupied all of the resources on the GPU, and MM1024 is barely able to launch any blocks at all until after MM256 completes. So maybe you've already figured it out, but we used 2 worst practices when designing our earlier experiment. The first dealing with the distribution of blocks to shader engines, and the second dealing with smaller blocks cutting ahead of larger ones. Before concluding, I'll go back over the first experiment now in a bit more detail. First, let's look at the impact of cutting ahead. Cutting ahead is the clear cause of the major slowdown in MM1024 when it needs to share CUs with MM256. Fortunately, proper partitioning prevents this cutting ahead by ensuring that MM1024 and MM256 aren't competing for the same CUs. As you may have figured out when I was describing how the ACE assigns blocks, it would be terrible for a single CU to be enabled on one shader engine, as every block sent to the shader engine must be executed using only this single CU. On top of that, we see here what happens if that same CU is also subject to a kernel with smaller blocks that can constantly cut ahead. So, to conclude, I'd like to dispel any wrong impressions. The point of this presentation isn't to criticize AMD GPUs, but simply to provide information. Clearly, when we know how this all works, we can avoid triggering the bad behavior. However, this also shows that total control over software is mostly useless without also having good information about the underlying hardware. Thank you for your attention.